Hello, this is Jonathan Gardner, and this is part of my Theory of Python series, and today we're talking about big O notation. People often poo-poo big O notation as some sort of interview question designed to trip up beginning programmers, but this is really an important topic, and if you want to be a good programmer, you really need to understand the concepts behind this. And it is also pretty common to communicate with other programmers using big O notation as kind of a language that we use to understand other people's algorithms. I'm going to go reverse here. I'm going to show you what big O notation means, and then I'm going to show you how we calculate it first. So big O notation is used for both the time and the memory that we might need to run a particular algorithm. Typically, these are the only two things people care about. How much time does the algorithm take and how much memory does it require to run? The big O's that you'll typically see include O1, which we call constant. It doesn't matter how many items are in the sequence or how big of a set you're dealing with, it'll take the same amount of time and memory. You might also find O log n, which we would call logarithmic. And by log, we typically mean log base 2 because we're in the computing world and binary is an important system. You might also run into O square root of n. I don't think I've ever actually seen that before, but it could exist. Then there's On, which we would call linear. The complexity grows in time, so if you want to process 100 times as many records, it's going to take 100 times as much time, or if it's On in memory, it's going to use 100 times as much memory to process. Then one other one that arises quite often is On log n, and this is base 2, of course, so we just call this n log n. You might also see quadratic behavior, On squared. And finally, you might even see exponential. So like O2 to the n, this would be exponential. I'm going to build a little chart here. As a baseline, I'm going to suppose that we have 10 items and it takes 1 second to run these algorithms. So each of these algorithms take 1 second. Or if we're talking about memory, it takes $1 of memory to run the algorithm. If we were to double the number of records to 20, then the constant algorithm would still require 1 second to run. Log base 2 of n would require 2 seconds. The square root of n would require 1.4 seconds. Linear would require 2 seconds. N log n would require 2.6 seconds. Quadratic would require 4 seconds. And exponential would also require 4 seconds. This doesn't seem too bad. In terms of memory needed, you'd still need only $1 of memory for a constant O in memory. You would require $2 of memory, $1.4, and so on. And $4 for quadratic and $4 for exponential. Things start to get a little hairy when you consider 10 times, so we're going to process 100 records. It still takes 1 second for constant. It will take 4.3 seconds for logarithmic. It will take 3.2 seconds for the square root. Linear time would require 10 seconds. N log n would require 20 seconds. Quadratic would require 1.7 minutes. And exponential time would require 17 minutes. How much memory are we talking about? Well, this is still taking just $1 of memory. This is $4.30. This is $3.20. This is $10, $20, and then we have $100. And finally down here, we're talking about $1,000. Let's take a look at what happens if we go 100 times. We're going to process 1,000 records. Still in constant time, 1 second. Log base 2 is going to be used 7.6 seconds to process. The square root of n will take 10 seconds to process. Linear time will take 100 seconds, which is about 1.7 minutes. And n log n will require 5 minutes, 300 seconds. N squared would require 2.8 hours. And this is insane, but exponential would require 2 to the 75 years. Remember, 2 to the 25 seconds is about 1 year. In terms of how much memory you need to buy, you still only need $1 of memory for the constant memory algorithm. $7.6 here, $7.60. $10 of memory here. Here you need $100. Here you need $300. And then here you need $10,000. And for this one, you need the insane amount of money, 2 to the 100. So we're talking in the neighborhood of Google. And if we went 1,000 times to 10K records, it would still take 1 second to process in constant time. Logarithmic time would take 11 seconds. The square root would take 32 seconds. This would take about 17 minutes. For in log n, we would need 1.1 hours. N squared would take 12 days. And finally, exponential would take 2 to the 975 years. And if we considered 1,000,000 times, so we're going to process 10 million records, it would still take 1 second. Let's do the cost of memory as well. So this is $1, this is $11, this is $32 of memory required. This is $1,000, this is $4,000, this is $1 million, better contact an investor, and this is going to be $2 to the 1,000. And for 1,000,000 records, it'll take 1 second in constant time, it'll take 21 seconds in logarithmic time, and the square root time will take 17 minutes. It'll take 2 weeks for 2 weeks for constant time. N log n would take 3 months. Quadratic would take 32,000 years. And this one would take 2 to the 999,975 years. And in terms of memory costs, this would still cost only $1 in memory. This would cost $21 in memory. This would be $1,000 in memory. This would be $1 million. 3 months would require $7 million. And this would require $1 trillion for the 32,000 year one for the quadratic. And this one, of course, would require 2 to the 1 million. So for this one, you'd have to contact the president. You have to get an entire nation to buy into it if you wanted to fund that project. Of note, notice that logarithmic time is actually more expensive in terms of time and memory than the square root. But at the higher end, it quickly shows a huge benefit, right? So when you're doing big O notation and you're considering what happens as the algorithm blows up, keep in mind that for small n, at the lower end range, there could be better algorithms that have worse performance at higher numbers. Oftentimes what you'll see is people will choose algorithms that are a hybrid of expensive and cheap algorithms. And they'll choose one algorithm when there's a few items, and they'll choose another algorithm when there's many. Let's talk about the formal definition of big O. It's not very complicated, but it's important to understand what it means. So in the formal definition of big O, we have two functions. We have f of x, which is the actual complexity. That's how much you actually need to run the algorithm in terms of memory or in terms of time. And we're going to say that this is equal to big O notation of some other function g of x. And what this means is that f of x is strictly less than some constant, it could be any constant, times g of x as x approaches infinity. We're going to use a small set of g of x's to describe these algorithms so that we can quickly compare many algorithms together. In order to calculate the big O, what we do is we take the f of x, we break it up into terms. After we've broken it up into terms, then we eliminate the terms that don't blow up the fastest. Or in other words, you just keep the biggest term as x goes to infinity. Okay? And then finally, we drop all coefficients, constant coefficients. Let's do some examples. So let's suppose our f of x is just a constant. It's like some number a. In that case, our g of x should be 1. If f of x is some constant times some variable, x, then our g of x is just going to be x. And if it's ax squared plus bx, well, this term is going to get bigger faster as x approaches infinity, so we'll keep that term and drop the coefficient, and that will be x squared. Let's suppose we have a log base 2 of x plus 10 to the x. Okay. In this case, the logarithm is going to increase, but it's going to flatten out after a while the exponential term will dominate. And so we'll just call that 10 to the x. And typically we'll write this out as 2 to the x, right? Because we use base 2 a lot in math and computer science. And another one that's interesting to look at, let's say we have x to the 1/2 plus x squared. And in this case, we're going to keep the x squared term because it goes faster. Okay. So that's basically how you calculate f of x and g of x. I'm going to show you some strategies I use to calculate big O. The first step is we want to find f of x. Okay, basically I want to count the number of lines run or the amount of memory. Keep in mind that 1 plus 1 equals 2, but big O of 2 is equal to 1. So if I'm adding numbers together like this, unless I'm adding them together n times, I'm just going to leave it as 1. So statements executed in succession like this is considered O1 in time. And if we have a fixed number of variables, that's considered O1 in memory. Okay, and that fixed number doesn't depend on the number of items we're talking about. Okay. 2, I note that if there's a function call, then the O is equal to the O of that function, right? So let's say I had a function called A, and I know that this is On, right? And so if I have a function B, so I have def B, and that calls A, then I know that B also has O of N, right? Because it's calling A, and that has O of N. The third thing to keep in mind is that when looping, it's going to be the number of loops. So you times by the number of loops. So you times by the number of loops. So like let's say I had a loop here. So I had while, true, and then I do some lines of code. And this code in here is only order 1, right? But if I'm doing this n times, then all together this is going to be O of n. Okay. As an example, let's analyze recursive Fibonacci. So recall that recursive Fibonacci looks something like this. So it takes some parameter n. If n is less than or equal to 0, it will return 0. If n is equal to 1, it will return 1. And then otherwise, it will return fib of n minus 1 plus fib of n minus 2. So in order to calculate the complexity of this, I first need to understand the behavior. So I'm going to propose a function called f of x. I'm going to use capital F. And this will roughly correspond to the number of steps to solve the Fibonacci. I should call it f of n actually, just to keep the notation consistent. So when f of 0, that just takes 1 step. F of 1 also takes 1 step. That's because it simply returns a value. But f of 2 is going to take 1 step plus the complexity of these guys. So it's going to be the same as f of 1, which is n minus 1, plus f of 0 plus 1 additional step. And f of 3, well, that's going to call f of 2, so it's going to do the number times for f of 2. It's also going to call the number of times for f of 1, and it has an additional step as well that it takes. And so we have the general rule that f of n is equal to f of n minus 1 plus f of n minus 2 plus 1, which is a sort of Fibonacci relationship. At this point, I'm going to use proof by induction. If you aren't familiar with proof by induction, you can review my basic mathematics video. But basically, all I have to prove is I'm going to assume that f of n equals some function, in this case, a of n minus 1, a to the n minus 1. And so I have to prove that f of 1 works. In this case, f of 1 is a to the n minus 1, which is a to the 0, which is just 1. And that checks out. And now I have to prove that f of n plus 1 is equal to that same thing. So that's going to be a to the n, given that f of n is true. Okay, so let's write this out really quick. So we have f of n plus 1, well, that's going to be a to the n, which is also the same as f of n minus 1, which is going to be n. So I take this and I subtract when I get n, plus f of n minus 2, so in this case it's going to be n minus 1, and we add additional 1 there. Well, we're assuming that this is a to the n minus 1, and this is going to be a to the n minus 2, and then we have 1 left over. We divide everything by a to the n minus 2, and so this gives us a squared is equal to a plus 1 over a to the n minus 2, but we're considering n as it approaches infinity, so this term drops to 0. We can solve quadratically for this, and we would get that a is equal to 1 plus the square root of 5 over 2. We're not considering 1 minus the square root of 5 because that would be less than 1, and we'll just consider a greater than 1. This is actually phi, the golden ratio. So we've proven that f of n is equal to phi to the n minus 1. So the order of this function is going to be O of phi to the n minus 1, but I'm just going to consider this O to the phi of n because this is the same as phi to the n minus 1 is the same as phi to the n divided by phi. So I'll just get rid of the factor of 1 over phi. So that is our order in terms of time complexity. How much memory does it consume? Well, when we're calculating the memory, we have to consider how much memory is used. In this case, the only memory that's used is the stack frame. And since we're not using tail recursion, the stack will grow at maximum with n. So the complexity in terms of memory is going to be O of n. So this is a terrible algorithm. We shouldn't be using it for large n at all. It might work fine for small n though. Let's now consider what happens for looping Fibonacci. This function looks very different than the recursive one. Well, the outside's the same, of course, and we still have that if n is less than 0, less than or equal to 0, we're going to return 0. If n is equal to 1, we're going to return 1. And then we're going to keep track of the two previous values, prev, and prev. And then we're going to loop as long as n is greater than 1. We're going to decrement n. And we're going to say the result is equal to the sum of the two previous values. Then we're going to rotate the values through. And previous is equal to the result. And when we've met that termination condition, we're just going to return the result. In terms of memory, this is rather easy. We only have 1, 2, 3 variables that we ever use. And so the memory for this function is just order 1, which is much better than order n. It uses much less memory. Whether we're calculating 1,000 terms or just one term, we're going to use the same amount of memory. Calculating the complexity of this, it's clear to see that there's no function call, so we only have to consider this loop, and this loop will loop basically n times. And so we consider the time complexity to be order n because it's going to loop that many times, more or less. And so this function is much, much better than the recursive function in terms of big O notation. We might also want to consider an alternative implementation called caching Fibonacci. What we would do is we would just cache the first n terms in memory, and that would obviously take O of n in terms of memory, and then we would look up f Fibonacci of n in memory, and that's just an order 1 operation. So it's much faster, but it requires a lot of memory. You might say, well, what if we only stored 1 out of 100 values? Like, for instance, we stored fib of 100 and then fib of 101. And so if you wanted to calculate Fibonacci of, like, let's say 120, it would work its way down until it reached fib of 101 and fib of 100. And we'd also store fib of 200 and 201, fib of 300 and 301, and such like that. The truth is, although this seems like an optimization that would be very good, you're going to end up with the same behavior. You're just storing 1/100th of the memory, which is still order n for memory. And it's still constant time, even though you might have to iterate up to 100 times to get the value. So storing a fraction of the Fibonacci series, it really doesn't make that algorithm much better. Another alternative, you might think, well, let's store like the logarithm, like log base 10 of n. So we're going to store fib of 0 and fib of 1, and we're going to store fib of 10 and fib of 11, and then we'll store fib of 100, and then fib of 101. And certainly this would use a lot less memory. It'd be order of log of n to store in memory. It'd also be order of log of n to find the next value, because you might have to count down up to log n steps to find the value. If you're really interested in a good solution for this, there is something called linear recurrence. That will give you even better behavior. You can look that up and see how it works if you want to. Hopefully this has been a good introduction to the Fibonacci, not to the Fibonacci series, but to big O notation and calculating how you might calculate the big O notation. Keep in mind that this is something that I use constantly in my job as a programmer. If you want to be a good programmer, you need to understand the principles behind this and learn the different algorithms that are out there. As we study lists, dictionaries, and other data structures, there's a set of algorithms that are always tied to these data structures, and so we have to understand their behavior so that we can always choose the best data structure for the job at hand. Anyway, guys, I hope you enjoyed that. Take care, and bye-bye. Thank you for watching this video on the theory of Python by Real Physics. Be sure to subscribe and ring the bell, like and share this video. You can find me on Discord or support me on Patreon. Links are in the description below. Thank you so much. Have a great day. Bye-bye.